Hello and welcome back to AI with Sally, an EE Times podcast that brings you inside my conversations with luminaries of the AI chip industry. Today's episode is brought to you by our sponsor, Synaptics. In today's episode, we're diving into one of the most interesting shifts happening in Edge AI, the move towards truly open, community-driven compiler technology. Embedded chip company Synaptics is open sourcing its compiler toolchain and inviting the global developer community to help shape the future of on-device intelligence. And they're doing it in partnership with Google. Our guest today, Dave Garrett, has been driving the strategy from the inside. We'll talk about why they're opening it up, how models actually get mapped to the hardware, what's wrong with chasing TOPS numbers, and what all this means for developers, for the edge ecosystem, and for the future of AI at the device level. Here's my conversation with Dave. Okay, Dave, welcome to the show.
Thank you so much, Sally.
So we're going to be talking a little bit about open source technology today. You guys have added Google's open source hardware IP to your AIoT products, to your new AIoT product line. But this isn't where the open source ends. You're open sourcing your compiler and your whole tool chain. Tell us a little bit about what exactly you're open sourcing and why you're doing this.
Yeah, well, thanks so much. It's a great, I say, some massive shift in the engineering community since I've been here 30 years in building chips. And we've always early on had proprietary tool chains. You try and protect secrets and you have your little niche and you stay there. And, I'd say over the last 15 years, the number of open source tools that I use to do my job has just exploded. And the world's community are working together towards best solutions. And you give away, I've given away some secrets, but what you actually get back is so much more out of that. So at the same time, when we look at our chips, we have an ML core, we need to have a proprietary compiler. And the answer is that actually slows down just about anybody else who wants to use our devices. So we're taking the approach now. We work with Google Research on the Coral NPU open source, accelerator. We're not, we'll show you what actually the accelerator is doing. And then our compiler, when we combine it with our Torque core, we're open sourcing the compiler. So now you get to see the interfaces and, really the secrets of what drives machine learning, AI models and how they get mapped onto the device. And what we expect out of that is we expect velocity for our company. We're happy to go show everyone, what's happening. And then you get a chance to actually contribute and fix. And then we have a certain number of resources in the company. Now you have this footprint, which is the world is helping us build something that's great. Everyone gets a piece of something very useful for them as well. And then, together we actually go much further. And fragmentation has been a real big problem. So fragmentation is, if I'm a customer, I don't know where to go next. And if I get stuck, I can't go anywhere. That's, another big thing about open source. So, really excited change. And it's not easy to pull everyone through this. I have engineers that go, no, you can't show that. Don't release that info. And then, hey, okay, what's the worst that's going to happen? We're going to gain more customers. That's a powerful thought.
Yeah, I kind of see the angle of having the community help you work out some of the kinks in your tool chain there. But if I am the customer and I'm thinking about buying a Synaptics chip and using it, is there a benefit to me as a customer if your stack is open source?
Yeah, absolutely. I mean, there is multiple ways to think about it. And again, the analogy I really love is in Silicon Valley. Why is Silicon Valley so successful? Well, you can quit your job and start another company the next day. And what happens is everyone gets very protective. But what it means is you're pulling in the best of what everyone else has done before when you're forward looking on that. Open source is the same strategy. If I'm a customer and I think about open source, like, oh, wait, that's dangerous. But guess what it's done? It's moved the tool so much further along than it would have been. And so you're getting benefit from even that side of it. It's way more advanced. It's better. It does more things. So you shouldn't be afraid. You should embrace it.
I guess I also kind of have the option to, like, if I see something that's broken or see something I want to change or, see something where I want to have an influence, it allows me to kind of be on the inside a little bit as well, right?
Yeah, exactly. I mean, I hate support tickets. Whenever I'm trying to do stuff, I'm filing and I can't get the answer I want. Most engineers are hands-on. if I can spend 5 minutes and look through some source code and answer a question for myself, that's velocity as well. And so we do see that. And, I faced that over the years where you can't find an answer. You're a black box. You don't know what's happening. Now with the tools, you can go and do, all kinds of triage early and quickly and move on. And you never have to worry about these tickets. And, by the way, generative AI tools, you can put in a set of code and ask what it does. And there's some amazing stuff with source code, what you can even, generalize and ask with generative AI. And so that's even, more reason to be open source. Why should I protect? If I obfuscate my code, I scramble it, Gen AI is just going to rip through it and tell me what's in there, no matter what attempts I do to try and keep secrets. And so let's just embrace it and go.
Yeah, I mean, it kind of seems from the outside like as you're just saying, open source can be a bit of a double-edged sword. Like there's a possibility competitors can kind of get in there and see what's in there, see what you've been working on. How do you balance those things, I guess?
There's all of those risks that happen. Yes, they see the check-ins. The check-ins reveal what's happening next. And so, we are very protective of customers' proprietary data, and we will firewall that, and we don't let all of our work show up in there. This is more about the open development and what our tools to do and our particular chips do. But we will firewall absolutely with the privacy and the use cases and whatever is important for customers. But I think the other piece of that is, you worry about revealing secrets, and then what happens is you still gain. Like sometimes you just gain by seeing how other people are doing things, and the community solves the problem. It's very rare that you're the only person in the world that's thought of something and deployed it, and you haven't benefited and stood on the shoulders of giants to get your job done. So, revealing more is a collective good, kind of feel, and that's the open source. People really started with the people that were saying, I've got society, got to be better. And they're not looking for any money and all of that. And so that's the bones of open source is let's make everyone better.
I mean, talking about a balance, open source kind of relies on the community to help, which can, I guess, as a company that helps you to get more done with less resources. And I know you want to work very quickly, but kind of on the other side, you're also limited by the speed at which the community moves. You're also kind of giving up some elements of control over this software and how it develops. How do you balance those two sides of the coin?
Yeah, I've seen people in open source, they get exhausted and they quit because people are demanding them as if it's a service, right? So that, I mean, Conda was a perfect example. The guy's like, I'm tired of you guys whining about my open source code. This is not my full-time job. So there is danger in that. Well, you have to pitch in. The answer is pitching in and upstreaming your findings is one of the key elements of a good steward of open source. And so demanding that you get all the benefit and you don't push anything back out, and you ask for this work to be done and don't contribute. That kind of goes against the idea. I mean, that's pitching in is really the key part of that.
So I'm going to ask you some questions about your compiler, a few little details on how it works. I know it's MLIR based. If you're listening to this and you don't know what MLIR is, it's an intermediate representation that's specifically for AI hardware. But MLIR itself is a community-led project. So I really wanted to ask you, to what extent are you dependent on MLIR developments and how that progresses as well on your own compiler?
Yeah, that's right. I mean, it is a really fascinating structure. Google, originally created this machine learning. It's intermediate machine language intermediate representation. It really is. Hey, the idea that there's all these different formats out there in the world, AI. There's PyTorch. You have the LiteRT, JAX, all of these things. Well, let's agree, and even Onyx, let's agree on a common format. So MLIR lets you take AI models from anywhere, put them in a common, representation so everybody can deal with it. So that's the first big change in the fragmentation. Well, I'm stuck in PyTorch. Well, no, who cares? You can represent your network in the PyTorch language, is easily imported into MLIR. And then now I don't have a training or a pipeline or a preference in my toolchain. And then Erie is the runtime and the compiler that can take MLIR and target, heterogeneous compute. And so that is, really it's a, Linux Foundation, Open Foundation project is supported, at the highest levels to make this easier across both data center and edge. And what it's doing is chunking through MLIR representations and giving you, the language to put in compiler optimization. So you can attack operators, you can attack, algorithms to make things better on your hardware. And what's neat is that it can target heterogeneous compute. So I can take a network, come in, target with LLVM CPU. I can target an ARM host processor and take the whole network and I can run that there. And then I can move portions of it over to a GPU if it's on the device. So I can mix and match how I want to do that. And that's where we fit in, is we then take torque deep, well past most of the optimizations in the generic compiler, code that needs to be there, and say, here's a dialect for torque. And I've got a network running on an ARM core, and let's take operators, and once the stuff that we do good, we move that over and we teach at Erie how to target our device. And now you end up with, this bytecode runtime that actually hits the silicon and does the real work. And you have the real opportunity to work within that framework. What's good about it as well is a compiler is an enormously hard problem. If you've ever want to take an NP complete problem where there is an infinite number of ways to attack any problem and you never know where the surface is, compilers let you go put your secret sauce in. So we even are happy if a customer has a network and there's a particular operator structure and the current code doesn't quite see this optimization that they have in their head, they can tweak that operator. Because it's forked from open source, they can keep that piece there and actually get an outcome that we even still can differentiate on open source chips that we sell to everybody. Customers still have their secret sauce through this community.
So my understanding is that MLAR was more developed for big LLMs and for big chips, but tell me about how well that applies to the edge. Is this something that's still being worked on, I understand? Yeah,
that's right. I would say if you take the mileage of MLIR and Erie, it's the big iron. Lots of big iron people are using that. And so, wherever you have mileage and you have most of the focus, that's where it's going to be the most reliable. So at the edge, we have lots of different networks that are showing up, and we have some, operators that's not supported. We got to tweak that. And that's part of the push, and specifically for us to be part of the edge community of Erie and help fix those things. So the networks that we care about, those operators sail through and upstream that, and then also optimize it, show how our torque core can do a great job on those things.
Yeah, we spoke about Erie just in the last minute or so, but I know one of the hardest things about developing an AI compiler or a compiler for AI chips is that often the compiler is expected to take on more of the hard work of mapping, especially with heterogeneous cores and so on. And I know you have more than one accelerator on your chip as well. So I wondered if you could go into a little bit about your strategy when it comes to mapping.
Yeah, mapping, really, mapping is an interesting exercise, and feedback is one of the most critical things. What happened is this is an experiment. I moved over to this particular core. What happened? What are the characteristics? How long did it take? How much of the resources gone? Is it efficient for that, hardware's, paradigm? And, we really do encourage you to run those experiments. Go see what happens. Hey, I move it all into torque. It's great. I don't have to touch anything. The GPU is free. No, this piece of this is a little bit more complicated control, and the GPU would be a good place because it's not raw convolutional compute. Think of that's a better place to do things without inefficiency. So the components of a compiler and the mapping, sometimes it's also reports and understanding what's happening, and then you can make, good choices. And the holy grail is, ultimately the computer sees those down the line. So every trick that every human has ever, put into an engineering problem, the goal is to make the compiler see that so you don't have to do that. that's an idealized view of the world, right? It never works quite that way, but we always strive for that goal, I'd say. So human innovation is still highly needed in compilers, and especially in this place where compilers for C code, 50 years of legacy it's gotten really, really good. We're in the early days, I'd say, of AI compilers for all these things.
With it being open source, though, if I'm listening to this and I really want to get stuck in at the lower levels and even have a go at mapping myself, I can access those lower levels with the stack that you're already talking about, right?
Yeah, exactly. So our compiler on GitHub, open source the code, you can compile the sources there. We have a Discord channel that the discussions on Erie can happen and questions and let's work on this together. And I mean, it's funny because Discord for me was what my kids played games on with their friends, and now all of a sudden we're doing serious work on gaming. What I thought was a gaming network, and it turns out it's serious work for a community to get together, virtually. And you used to have to sit in a room together to work on these problems, and now we've got these tools that you really can be anywhere and still be a meaningful part of a community.
Curious about what the hardest things are about mapping. I know it's not straightforward, but as models get bigger as well, it's more like you have to break it up into more chunks and so on. Like, what are the challenges? And especially as models get bigger, what are the big challenges?
Yeah, it's a great question. So, we get, neural networks are organized into, layers. So hundreds of layers of things of compute and, all kinds of things. But what happens when that particular layer doesn't fit on your accelerator? And that is one of the key things. Like, I've got, 2 megabytes of intermediate activations, and I've only got 512 kbytes of on-chip memory. So you end up, we call that tiling. You've got to break the problem up and attack part of it. Well, now it gets tricky because let's say I take an image and I break it into 4 quadrants. Well, there's some overlap. So now you got to manage, well, what quadrant? There's a little bit of overlap if I want to make it look mathematically continuous. And then I've got to pull that in, put that back into memory, cache the next thing, work on those chunks, and deal with all those overlaps. And so tiling is one of those really hard problems. How to take what the AI engineer thinks is just, this is an amazing network. And you're like, well, you didn't look at the memory, did you? But our job is not to say, go change your algorithm. We know the performance of AI is hard to do as well. So our job is to go say, hey, well, okay, given the constraints, tiling, how do I break problems apart? You will trade memory bandwidth for compute. So if I had everything in the memory, I'd be much more efficient in compute. So that is where the compiler comes in. Making hard decisions on compute, movement of data, how do I store? And then there's another thing is, well, you always look at a network and it's a sequence of layers. The other artifact is you punch through a bunch of layers. Like I can do 3 or 4 layers deep on a subset so that I'm not even streaming intermediate things out there. So now I've given you another vector space, which goes to the NP completeness. Right? How do I make all these choices? That is the crux of the compiler, is making hard choices with constraints. And what Erie does is it gives you the toolkit to make those algorithms and decisions, and it's your job to figure out how to present that. And like I said, back to think, every general purpose compiler that's trying to do many different things won't see your particular case in a particular optimized way. If you see that, go fix it. Go tweak it for yourself, because we haven't considered that infinite space.
I mean, the ultimate result of all this mapping, or the result of all of these hard choices, is being able to efficiently use our TOPS, being able to use our compute efficiently. Can you give us an example of how much difference good mapping can make?
Yeah, I mean, look, you'll see, when you can pack a convolution, you're easily using almost all of a multiplier accumulates on a chip can be packed optimally. Now, that's still, convolution has kernel sizes, and they have depths, and there's prime numbers. And so those, we'll say computer architects love powers of 2 binary numbers, and it's just is baked into the way we think, right? So when you have an AI person that thinks a prime number is a good size for a kernel, there's the conflict there. So you do multiple ways, like 3x3 kernels show up everywhere. So that's 9, but the depth can be 128 depths of channels. And so how you map, you still can get really high efficiency on these multiply accumulates. But then, these, ResNet 50, everyone loves to go benchmark that because that's the first thing. But I call that like the first generation of networks. It's really simplistic and it just puts compute at the problem, and it's not smart about what it does. Even the modern YOLO V8, we're mapping that on our devices. What you see is convolutions, and then there's triplets of sigmoid activations, which are 1 over an exponent of e to the power whatever. So this is now not a thing that a Mac does well, and that's integral into the performance of these models. And so we have to be really great at convolutions, and then you switch to this activation, which doesn't fit that box of raw horsepower, and we're building things into our torque compiler to do the sigmoid great. But if you ever went to TOPS, you're like, oh, why are you so slow at e to the minus x? That's just one operation. It's a terrible metric of an exponential, which is really harder to do in hardware than multiplication.
Yeah, I mean, obviously, I talk to a lot of AI chip companies, and I do feel like TOPS is a kind of a useful back of the envelope comparison. What about TOPS per watt? Sometimes as a comparison point. Do you agree we need something to say how to give us an idea how big a chip is to start with?
Yeah, I mean, look, we have this debates all the time. Like, oh, TOPS, it's a terrible metric, and we're not going to report TOPS. Well, you go out to the community, everyone wants TOPS. So you're fighting a game. So it's very hard to go fight that TOPS inertia because it is an important metric. But what we focus on in the education is, well, neural networks are really complex now, and it's more, compute matters. It's one of the important vectors. But it's the delivery of data, it's the memory bandwidth, it's the new activations and layers that actually have to do exotic things. And so we have to think more about, am I getting the job done for these really modern neural networks? And that's where we try and focus on, like, hey, let's go take a look at your real problem and say, okay, am I computing that? And if you have sometimes a TOPS number, like a DSP can have a huge TOPS number, there's no physical way to feed those multiplies at the same rate that they claim the peak TOPS is there. TOPS per watt is even worse. What they try and do is isolate the multiply and say, hey, I've got this extremely low power multiplier and accumulate. And guess what? You're forgetting about the memory subsystems and the prime number, multiplexers and all of the delivery systems that make TOPS per watt on your particular multiplier irrelevant. And then, TOPS per watt also, we know in the tech field is a geometry game. So if I'm in 2 nanometer, yes, I've got my dynamic energy is going to be smaller for a multiplier, but I don't necessarily have $800 million to tape out that, that particular chip for the edge. We're not going to use 2 nanometers. So why say, well, 2 nanometer chip is going to be way more power efficient at the edge, that ignores all the economics of all the other things that go into, the edge is not going to pay that $1 billion premium that NVIDIA does to get their highest performance TOPS per watt chip.
Yeah, completely get it. I understand where you're coming from, especially as neural network operations get more complicated, but I am going to reserve the right to use TOPS as a shorthand for big chip or small chip. It's like, I guess I'm not going to try and compare like 26 TOPS to 25 TOPS or something like that, right? Yeah,
that's right. And look, and that's the ultimate conclusion. As much as we don't like TOPS, it is a common metric. It gives you the first order rule of thumb. And I love rules of thumb. It really does help you understand things. And then the brainstorm is, how do we report efficiency for real complex problems? And that's the nuance that's coming. And like, you look at DeepSeek, what DeepSeek shook the world. Well, what did they do? They took the additional step, kind of like the analogy of ResNet, which is raw horsepower. They said, well, I have billions of parameters, but you know what? I can be smarter about not using all of them. So now neural networks, AI models start to look conditional. And we see that in Gemma 3 from the Google's team. It's a conditional execution. And what I love, my friends in Google Cloud, he was saying like, okay, 2 years ago, we would plan for a 20 billion parameter model. Today, it's a 2 billion parameter model. So same performance, right? So this is, we've never seen this. This is faster than Moore's law, what models are able to do because of smart architecture. Smart architecture means complex, means decision-making. And a perfect example, the Coral NPU in our Torque core, it's a RISC-V. So we have the ability to actually put, smart decisions that don't exist in data paths, future-proof. We can decide, hey, we'll actually make some really cool decisions. We'll take advantage of that, the traditional compute paradigm to make decisions. And I do think that's how AI in a year from now, like the 100 million parameter model, you're going to be blown away what that does at the edge. What we do is let's prototype, 2 billion parameter models today to figure out what we want to do on our chips. And we'll know that somebody magically is going to help us with a model that's going to show up in 2 years and help us. And I think even, when I hear the OpenAI team, the origins of that company is they looked at the metrics early on for LLMs, the original ones, and they drew this projection that said, hey, if we put more compute and more training, we actually have this curve that doesn't stop. And you take for granted today that they're the winner, but they took the bet to go buy 16,000 GPUs and just prove that out. And they didn't see, they had an experiment that said that was true, and they proved that out. It's that's what we expect is whatever's at the high compute today, wait a year, it's going to be lower.
Yeah, it's going to come to the edge. Okay, if someone's listening to this and they want to write some kernels, or they want to have a look at your code or get involved, join your community, where should they start?
Yeah, developer.synaptics.com. And every time I give a talk, that is the landing page that will get you everywhere. So we have, kits that you can order next day, be at your desk. It's going to have the links to GitHub pages where the compiler and the open source tooling is. And then that'll give you we have quick start tutorials, 5 minutes in on one of our Makina kits, you are running AI and you can start to play with it and get a feel. And, that's the odyssey we want people to go through is like, do the simple stuff, learn, get the feel for AI. And then we're giving you an easy Python class to run the models. Well, there's a C API underneath that. You start to peel the onion when you really want to go to production with something. Developer.synaptics.com. Everything is the landing page. And if there's one thing that you remember for today, remember that URL, and then you can recreate all of what we've talked about today.
Perfect place to finish. Thank you so much, Dave. Really enjoyed having you on the show.
Yeah, thanks, Sally. I really enjoyed this too. And, great questions. I love this stuff. It's we're having fun at the same time that we're building, cool things, and trying to educate the community is an important part of this.
Thank you very much, Dave, for the fascinating conversation. This episode of AI with Sally was brought to you by Synaptics. And thank you very much, Synaptics, for sponsoring us. If you want to learn more about Synaptics' Astra platform, its open source toolchain, or anything we've been talking about today, please check the links on the podcast page at eetimes.com, where links to articles and topics we've discussed are shown on your left. That brings us to the end of the episode. Please tune in again next time for more conversations around AI, silicon, and systems. AI with Sally is brought to you by Aspen Core Media. The host is Sally Ward-Foxton, and the producer is James Eade. Thank you for listening.